This is Kylie McCook, and this is my physics lab. So the purpose of this experiment was to first calculate the mass of the black hole through the net force on the star due to the black hole and the position of the star and its trajectory. Second, we wanted to determine the initial velocity the ship must have to fly closely around the black hole without crashing. And lastly, we found the initial velocity the ship must have to orbit the black hole. And this is a little preview into the data that we ended up collecting in the lab. So some important equations, first starting off with the Newton's law of universal gravitations. This allows us to find F-grav between two objects in space. These parallel and perpendicular equations allow us to find F-net parallel and F-net perpendicular and also add them in order to find F-net on an object. And then over here on the right we have Newton's second law, which shows how F-net is equal to mass times acceleration. And then down here we have the velocity update formula as well as the position update formula. So some initial conditions going into the first experiment is that the mass of the star was 2e30 kilograms. The first data point is at t equals 0. Our delta t is 86,400 seconds, which is equal to 1 day. Our gravitational constant is 6.7 e to the negative 11. Our system is the black hole, and our surroundings is the star. So Newton's second law whenever it comes to finding the mass. So on line 175 we found F net, which is equal to the change in momentum over change in time. And lines 178 through 183 showed the parallel component, which is just equal to the change in momentum of the parallel component. And then line 186 through 189 shows the perpendicular component, which is just equal to the change in momentum over change in time for that particular component. And then line 193 shows the calculation of the mass of the black hole. So our results whenever we were finding the mass was that it equaled 1.46832 times 10 to the 34. And then over here on the right, this shows the trajectory of the spaceship, where the blue arrow is the perpendicular component, the purple arrow is the parallel component, and the orange arrow is our F-net. So going into the second part of the experiment, our initial conditions: the system was the spaceship, the surroundings was planet and black hole, and then our initial velocity is unknown. And the screenshot shows the constants that we knew going into this part of the experiment, as well as the initial conditions. And then here is the code applications for the velocity of the black hole. On line 72 we're finding r, on line 73 we're finding r hat, and on line 74 we're finding F grav using Newton's universal equation for the force of the black hole on the planet. And then down here on line 80 we're finding the F net on the planet by adding the force of the black hole on the planet and the force of the ship on the planet. And then down here on line 102, this is the application of the velocity update formula, as well on line 105. And on line 103 we have the application of the position update formula, as well as on line 106. And our results for the initial velocity was negative 3.49 e to the 7, 3.64 e to the 6, 0. And some possible errors throughout this experiment was for mass. Was that mass we should have ran the code for a longer time, so I had more data to average. And for the velocity component, the decimal point accuracy of the initial velocity might not be as precise as we would like due to a guess and check method trying to get close to the black hole. So for the what if part of the lab, we wanted to see what initial conditions we needed in order for the spaceship to enter orbit of the black hole. And so we knew that the spaceship had to have a similar initial velocity to the planet in order to enter the orbit, but it needed to have a smaller x component and a larger y component. So we ended up getting negative 1 e to the 6 for the x component and 1 e to the 7 for the y component. So ultimately, what does this mean? The net force and the rate of change in momentum are equal values under Newton's second law, which is the change in momentum over change in time, is equal to F net, but they are not necessarily the same thing. So net force describes what is changing the motion of the object, while the change in momentum describes how the motion is changing. So both have parallel components in this experiment that affect the speed, but our net force is the only one that has a perpendicular component that affects the direction. And that is the end.